Okay, let's go over section 1.4. Okay, section 1.4, Euler's method. Okay, so Euler's method is a fundamental way to find approximate solution to the differential equation. Okay, so many numerical methods for solving differential equation, but Euler method is a really fundamental, but starting point to enter the numerical way method. Okay, to study. So. Okay, let me give you just the blueprint of the Euler method. Okay, so right here, we draw this. Okay, so let's say this is a solution chord right here. Solution chord right here. Or we can say integral chord, solution chord, whatever. Okay. Yeah. Now then, so here is a T0. I mean, here is a T0 right here. This is T, and then this is Y. I mean, we're talking about the differential equation dy dt is equal to f of t comma y. Yeah. Okay. So right here, this is the initial condition y0, y not. Okay. So if subscript 0, or sometimes we call this one as y not. That means that this one, y not. Okay. All right. So initial condition given right here. So this is a particular solution. Okay. So y of 0 is it? Oops. Y of t0 is equal to y0. So this is initial value problem, IBT. IBP. Okay. So to a second right here. Okay. So now the we wanna give me a second. This one. We just draw the short line segment like what we did in direction field. So like this. Okay, right here. That's the slope, right? Of the tangent line. This is the tangent line at t0 comma y. So t0 comma y0, isn't it? Okay. So let's figure out the equation. I mean, the formula of the tangent line. This one. Okay. So y then using the slope intercept form, because this is line, right? So we know the equation line, right? Point slope or slope intercept, right? We want to use a slope intercept form. A point slope, sorry. So this y minus y naught is equal to the slope m. What's the slope? dy dt, isn't it? Which is f of t comma 1. So here's the slope m, sorry. So this guy is equal to dy, I mean y prime, right? Y prime, but this is a dy dt, right? But this is equal to f of t comma 1. So m times, and then what? T minus t0, t naught. Okay, so it means that y is equal to df t0 comma y0 times t minus t0. Oh, I missed this one. Y is equal to y naught plus, sorry, t minus t0. Okay, right. So using this one, we can predict, we can approximate what? The solution, the solution at t right here, maybe t0 plus h. Okay. So we assume that we don't know a solution y. Means that we don't know integral curve. Okay, we do not know. We assume that we do not know integral curve. So right there, which means that this is y. Let's say y sub let's say this is equal to, sorry, this is a t, let's say t1, which is a t0 plus h. H is kind of short, a small, the value kind of 0.1 or 0.01, something like that. And then let's say this is the y of t1. This we don't know. We assume that we do not know because we do not know integral curve, because we do not know solution. We do not know solution, but we can approximate y of t1 using tangent line, whose equation is this. Which is right there. Let's say this is a y sub 1. So what's y sub 1? Y sub 1 going to be what? Y sub 1 is y0 plus what? There's an f right here, right? And the f of t0 comma y0 times what? t1 minus t0. Just evaluate this one at t1, right? So that can be used, this one then can be used as approximation of y of t1. That's the exact solution. Exact, so let's say just S or L represent the solution, the exact solution at t equals t sub 1. Okay. Now you see that, right? There is a gap between the approximation y1 and the exact solution y of t1. I know it's a lot of gap. You can see that there is a big gap, but we can use this one as the approximation. And then we know that when h approaches 0, h is really small and small number, so that t1 approaches t0, then this gap will be decreased. So y1 will be really good approximation of y of t1. Okay. So now then, once you got this, then now what? What are you going to do? At this point, we're going to find the slope of tangent line again. Here. And then we find, and then also we're going to, give me a second. This one. So let's say right here, this is going to be T2, which is a T0 plus 2 times H. And then here's a point right here. So this is going to be Y sub 2. Okay, we're going to get another the tangent line, this line. Okay, this is going to be what? Then y2 going to be y1 plus, see that this is y1. This is the approximation of a y of t1, okay? Then f of t1 comma y1, and then t minus t1. T2, right? T2. This is going to be approximation of y of t2. Repeating this process, then y sub n going to be n plus 1 is going to be y sub n plus f of tn comma y sub n, and then tn plus 1 minus t sub n. This is approximation of what? Y of t sub n plus 1. So this is the what Euler's formula. That is Euler's formula. Okay. So I'll give you an example. Before giving you example, actually this is what? That's the, is it really similar to the Taylor's formula, Taylor's polynomial, Taylor series, I mean? Taylor, or you can say Taylor polynomial up to first order. Yeah, this is actually we can derive Euler's formula from the Taylor's polynomial. Remember Taylor formula? Y of t is equal to, right? And then y of what? For example, n plus, right? And then what? dy dt. Let me use this one, y prime. Well, y just first derivative, and then at tn, right? over 1 factorial, right? And then t minus tn plus y second derivative tn over 2 factorial, right? T minus tn squared and so on. This is Taylor's polynomial. So we cut here. This is exactly the same as this one, right? That's a Taylor's polynomial. What? Taylor's polynomial centered at t is equal to t sub n. Taylor's polynomial, yeah, centered in t sub n. So, but here's a question then. Can we just use the more? Because look at this. There's a sort of peak, some kind of, we can clearly see that there is a, gap right here. To reduce this gap, we may use a more term than, this is not going to be line, but this is kind of curve. So that point close to this. Yeah, that's a Taylor's method. So Euler's method is the degree 1 of Taylor's method. So Taylor's method is a general method than Euler's method. Okay. So we talk about Taylor's method in chapter 2. Okay. So, but I just give you some short introduction. Okay. You don't have to understand this one at this point, but this is Euler's method. Okay, you should keep in mind that. So it's the example. Let's see example right here. So this is Euler's formula. Give me a second. Let's see. All right. So starting point. So here we assume that the initial condition is given. Okay. So step 1. D0 and the Y0. Okay. This is the initial condition. You just, just nothing but initial condition. The step 2. Euler's formula. Yeah, we apply Euler's formula. Oop. So y sub n is equal to y sub n minus 1 plus half of t sub n minus 1 comma or y sub n minus 1. Then t sub n minus t sub n minus 1. We can just say y sub n plus 1, just one step up, okay, to n plus 1, okay, doesn't matter. So, and then t sub n is what? T sub n minus 1 the plus h, or this is equal to what? N times h, right? N times h. H times that. Okay. And then y sub n is here, the y sub n. This is the approximate solution. Solution at t is equal to t sub n. Okay, so now then t sub n is going to be t0 plus n times h, right? Because here in the n goes 0 and then 1 through d, maybe, the n. Because anyway, we have to discretize the time step, okay? For example, here's see here, this is t0, normally 0, because initial time to the, let's say this is a final last time. Let's say this is a t sub n. Okay, then this is going to be t sub 1, here's a t sub 2, here's a t sub 3, blah, blah, blah. Maybe here's t sub n right here. Okay, so discretize, in Korean, discretize 이산화. Okay, discretize the time interval to n steps. And then y0, this is initial condition, right? This is given. Okay, and then do this one. Okay, apply this one right here to here. Okay, y sub n plus 1 is equal to something. This is all the formula I gave you, right? So I'm not going to write here once again. So easy example. So differential equation is going to be the y prime is equal to minus 1/2 y and then minus t and then plus 3/2. Okay. And then y of 0 is equal to 1. Okay. So I think you can do that, right? Following this, I can help you. Just try to find out approximate solution at with the h is sorry, this is 0.2. There's a 0.2, and then find out y sub 1, y sub 2, and then y sub 3. Okay. And finally, just find out what yeah. So just can you do that? Then I can help you. Okay. So let me turn on the recording. 1 second.